Welcome to the UEI Technical Masterclass. I'm Bob Finn with UEI. I hope everyone here is doing well today. Today's webinar is entitled The Art and Science of Grounding and Isolation. Our presenter will be our own Timur Raza. In this class, Timur will provide useful insights into avoiding unwanted noise in your high precision application. As I say every week, I want to remind all our webinar attendees, this is an interactive environment and we encourage you to ask questions. So if you've got a question, send it our way using the webinar chat tool. And I think that about wraps up my introduction. So without further ado, I'm going to hand this over to you, Timur.
Okay, so hi everyone, my name is Timur. I'm an applications engineer here at UEI. And I thought a good place to start was this image right here. So this is actually a photo taken from the top of a Boeing 737. That glow you can see in below the clouds is actually lightning forming. So when an electrostatic charge builds up in clouds, it can reach levels of 10 to 350 coulombs, depending on the size of the lightning bolt produced. This naturally ends up ionizing the air, which produces that glow that you see, and also ends up creating a whole lot of electric potential. Current will always take the least resistant path to ground, but sometimes all paths are pretty high resistant. In this case, a lightning bolt travels through the air itself to ground itself to the earth. So what I'm kind of getting at is that what if the target of this lightning is your precision system? How do we keep ourselves safe in dangerous scenarios? How do we take advantage of grounding and isolation methods to make sure that our application or DAC system is both safe and precise? All right, so that kind of gets us into our agenda for today. We'll first characterize some of the different kinds of noise you'll commonly see in your application. We'll talk about keeping and breaking isolation, some of the anti-noise features that we have that help combat some of the noise types that you'd see in your application. We'll also talk about guardian features and some good practices you can take advantage of to really maximize your input precision. And then we'll go into questions. So to preface this talk, we're going to be talking about isolation in two different senses of the word. The first is the engineering sense, where you keep one signal isolated from a different signal, and therefore something that happens on one signal can't leak over to the other signal. But we'll also be talking about it in kind of the more abstract sense, which is isolating your signal from the noise sources around it. So let's start by talking about these noise sources that you commonly see in your application. Here are some nice graphics about the 5 kinds of noise we'll be talking about today. The first is mains noise, or more generally, transformer-based noise. When converting from AC to DC, there will naturally be some ripple. So one option that you can do is spend a whole lot of time and development resources removing this ripple and making it down to a 1% or a 0.01% or some infinitesimally small percentage of that original ripple mirrored in your DC output. The second kind of noise that you might see is thermal noise, or Johnson-Nyquist noise. Basically, heat affects all different types of charge carriers, but certain types of sensors are particularly susceptible to thermal noise, such as strain gauge sensors and piezo vibration sensors. In this case, because those sensors are analog and specifically leveraging various kinds of physical phenomena, introducing heat to that scenario often throws off that sensor's calibration range when interfaced with the digital system. So we'll have to figure out how to avoid heating up the sensor as well. The next kind of noise is induced noise, and this can take one of 2 forms, capacitive or magnetic. You'll often see this in high power EV or electric boat applications, as well as in long power lines. Anything that has the potential to behave as an antenna and can pick up ambient noise typically will. The next kind of noise is crosstalk, and this is more of a board level noise, whereas induced noise pulls in noise sources from the external world. Crosstalk is present mostly in mux and high current applications, where an adjacent channel will try to leak its output signal into the mux signal that you're currently trying to read out of. And the last kind of noise is radiative noise, and you'll mostly see this in space. So let's start by characterizing some of the isolation features and scenarios that you'll commonly run into. So here's an example of one of our chassis. As you can see, we have the backplane on one side, which is how all of our I/O boards and CPUs communicate. And one step above that, we've got I/O boards. And as you can see, there's two different kinds of I/O boards here. One of them is isolated, which contains isolated channels on board the I/O board, and the other is not isolated, which doesn't particularly differentiate between the sensors that are attached to it, which doesn't keep isolated or separate the sensors that are attached to it. What if we were struck by lightning? So the idea is that we can use this model to kind of talk a little bit about the ways that a lightning strike might propagate throughout the system. Let's say we were struck on sensor 0. As you can see, the area of effect would be the adjacent sensors and the board itself, because a non-isolated board and the channels on that board can be considered one and the same thing. However, because there's an isolation barrier between that board and the backplane, this one lightning strike has a very low probability of propagating throughout the whole system. So this is one area where a low level of isolation can still protect the other boards on board your chassis in a worst case scenario, such as a lightning strike. But we can get even more granular with it. Let's say sensor number 2 was struck by lightning. What happens? In this case, because the channel is isolated, the only thing that is affected is that isolated channel. There's a very low possibility of the I/O board itself or any of the adjacent channels being affected by this lightning strike. And there's an even lesser chance of that strike traveling through the backplane into the other I/O boards. And this is a very good place to talk a little bit about something we see very commonly, and I think would be helpful to address now. So let's say you're doing your due diligence with your system design, and you've decided, that you need to prevent all of your ground loops, that you'll dot all of your I's, cross all of your T's, connect all of your grounds. In most cases, this is a good idea. However, in this particular case, it's actually a mistake. When connecting the grounds across two isolated channels, what happens is that there's now a path between the two channels that is created that would allow for something catastrophic, like a lightning strike, through which to propagate. So in this case, if sensor number 2 was struck by lightning, you can see that now that because there's a path from channel 0 to channel 1 can also be affected. However, the I/O board itself will not really be affected, and the backplane will probably not be affected either, because the only connection path between the two channels is through that ground. And another point to be made here is that, again, it depends on those paths. So if only channel 0 and channel 1 are connected, then only those two channels will be affected. The other channels on that system will be all right. But again, this gets into a very good kind of discussion of the system design involved. So now that we've covered this case, let's talk a little bit about the other anti-noise features that are involved in UEI systems and how we can leverage those to minimize any effects that we might see in the field. So the first one, as I covered in the past few slides, was the isolation barrier. And this would help us in the most catastrophic scenarios. However, we covered different kinds of noise earlier. So another feature that we use is pulsed excitation. And what this does is it actually pulses the excitation to every individual sensor that can be affected by heat effects, such as your strain gauges or your thermocouples. And it allows those sensors to cool back down, which keeps the sensor within your calibration range and prevents your measurements from becoming less and less accurate over time. Another method we use, we provide differential inputs. And this allows you to get a differential measurement, well, an original measurement that is independent of any noise that affects that system. For example, the wiring or ambient induced noise, and allows you to produce the original signal again from a hardware perspective. Another method that we have to make ourselves aware of noise or non-isolated or feed-in effects would be the Guardian series. So we can talk a little bit about the self-check features, but really what I want to focus is the real-time diagnostics here. So the open and broken sensor detection, as well as self-test, are really the most important things here. Figuring out if your sensor is open or broken due to, let's say, a lightning strike, as we've been discussing throughout this masterclass, is a good first step. You know, we can retroactively figure out if something happened and be able to work backwards and figure out the area of effect. Additionally, self-test is also a good way of retroactively figuring out what's going on, which kind of gets us into the third and most important diagnostic feature, which is circuit breaker functionality. In the case that we can pick up what's going on fast enough, and in most cases, this is an underlying feature that will happen either way. Some of our boards can actually shut themselves off and isolate themselves from the output, which may help survive certain levels of lightning strikes, as we've talked about. All right, so now that we've talked about the features that we have, let's talk about some good practices that you can leverage that will also help you keep your system as precise as possible. So some good practices, and many of these are pretty generic and can be used anywhere, which is kind of what I was going for on this slide. The first is twisted pair wiring. Naturally, this will allow both of your input wires or communication buses to pick up an induced noise source, which will allow you to differentially filter out that noise. Another one, and this is pretty big advantage of the UEI cube system, is short wire lengths. So of course, not only do long wires pick up noise pretty easily, but they're also expensive. If you have a very long heavy gauge power cable or thermocouple wire, that does become pretty expensive. So being able to wire all of that to a CPU input interface system that is ruggedized, such as the cube nearby, helps address two problems at the same time. You can eliminate miles of cable this way. Another one is frequency selection, and this becomes more important with multiplex inputs and outputs. Only inputs. So with multiplex inputs, crosstalk becomes an issue when the mux is no longer able to keep up with the frequency selected. We see this in arbitrarily high frequency selections, such as 100 kilohertz. We find that a good way to address this is to select the frequency based on the Nyquist rate or some measure above that Nyquist rate. So 2 times the Nyquist frequency or 10 times the Nyquist frequency, if you're looking to be very precise, but also create a good balance of crosstalk elimination as well as signal characterization. And the last thing is we covered in this presentation is to keep your isolation barriers as best as possible. Now, of course, I understand that there's cases where this may not be possible. Maybe you have a specialized sensor that joins 2 different types of sensors to give you one important output, or you're using a 9DOF or something. But the idea here is to keep your isolation as best as possible and understand where those barriers can be used and where the area of effect and containment is. So that gets to the end of my presentation for today. I think we can jump to questions now. Let me take a look to see what we have. Okay. Oh, we have plenty of questions. Okay. First question: is it default for your DAC that the I/O boards are isolated from the backplane? Yes, that is a default feature that we provide on pretty much everything. The I/O boards are all isolated from the backplane via a 350 volt isolation barrier, I believe. The other isolation methods that we use are on a case-by-case basis, depending on stuff like speed, current, and other factors. We use methods such as optical, magnetic, and capacitive isolation. What is a good approach for grounding isolated channels? Okay, this is another good question. So you can think of an isolated channel as its own return, as its own input and its own return. So the idea is that that channel would behave as its own circuit, right? Its own current loop. So as long as channels weren't grounded to each other, you wouldn't be connecting one loop to the next loop. I hope that answers that question. Regarding differential inputs, if the data acquisition system is in a high noise environment, we've noticed that the ground reference of our sensors exceeds the allowable range of the DAS. I'm not sure. Our solution has been to use a bleed resistor and inductor to keep ground references related, but provide some form of isolation between the different input ground references and the DAS ground reference. I'm guessing that DAS is some form of input device or output device. Is there a better way of designing this ground isolation? We can get back to you on that particular question. I think this one's a little bit longer and would be better served in an email. All right. Let's see. Next question. In which range is the pulsed excitation working? It depends on the sensor. I believe we use different ranges for RTDs and thermocouples and so on. Where does shielding fit into noise reduction? Well, so for this question, I think typically you'd want to you'd want to connect the shield of a certain wire to the ground of the source, of the output source. So that way you'd at least reference all of your signals to the same input, well, to the same output, which would allow a differential input to be able to filter out anything that came in and provide a bit of a capacitive effect, I think, which might help. So yeah, shielding. The go-to answer for shielding would be to ground it to the source when using us as an input. However, there are cases in which maybe you'd want to take a different approach with it. It is a very case-by-case kind of question. So yeah, if you have a specific question on that, feel free to send us an email. We'll follow up with you on that as well. All right. Further questions. Is there any difference between isolation options on each chassis? No. Chassis level, the flat rack, the cube, rectangles, and all the mill chassis variants of each of those form factors are all the same from an isolation perspective. You still have the 350 volt isolation barrier on the backplane, and different boards that have different isolation options will still have those in their mill variants as well. How does isolation on an AO work? All right, that's a similar question to earlier. So again, you can think about it as kind of a voltage or current loop that is ground isolated from the other channels. So that AO ground will be isolated from the other AO grounds. So the idea is that if you shorted one AO channel, then the damage from that shorting would be limited to that one loop. It wouldn't be allowed to propagate out from that particular AO channel to other AO channels. Is digital isolation possible? Well, okay, I guess this question is aimed more at buses and those types of protocol, specific bus level wires or very long bus wires. And I mean, the answer is yes and no. It's an interesting question. I think the clearest answer would be on a board such as the 433 or 432. If we were really stretching, you could use the circuit breaker functionality to cut off whatever the output of that particular channel or input of that particular channel is, if it went beyond a certain current range. However, I think with these kinds of specialized interfaces, it is again very much on a case by case basis. You know, USB will be different from RJ45. Okay, are the I/O board's power supply outputs ground isolated? Again, this depends on the board itself, right? So if this is an isolated I/O board, then yes, the power supply ground will be isolated from each channel ground. However, if this is a non-isolated board, then typically ground will not be isolated from from each of the output grounds on that particular I/O board. So again, this is also a very case by case basis question. I guess the one other case where this would be relevant would be using the PC91X or 90X series power supply output boards. And I believe those are also isolated from the backplane. However, once you connect those into a board that might need, further power, then in that case, isolation would, in that case, something that would affect that power supply board and its connected board would affect both of those. Right. For isolated channels, the ground is going to be tied together at some point. Should each channel ground have an isolation device in line? Again, this depends on what kind of board you're using. If you're using a standard isolated I/O board, then we handle all of the isolation and the grounding on our end. So internally, yes, there's some form of power transfer that is, I believe, transformed usually, that we handle internally. However, that said, for let's see, should each channel have an isolation device in line? Yeah, again, I think that depends really on what you're trying to do. If you're trying to connect to something externally, right, from one channel to that external device, then yes, you do need to ground those together. However, if you're trying to ground two adjacent channels, right, let's see, ground 1 and ground 2, for example, then I actually wouldn't recommend grounding them together. That would, our internal isolation features that I mentioned earlier, the capacitive, transformative, and optical isolation methods do handle all of that grounding on the board itself and on the backplane. I hope that answered that question. Didn't rant a little bit too much. Are there any other questions? Going once, going twice. All right, Bob, it's all yours.
All right, a few things to note. Our next master class will be September 10th. And this particular session will be a joint class with RTI and the MathWorks. So stay tuned for that. We record every webinar, post the videos online. You can find these archived masterclass videos on our YouTube page or on our own webpage at ueidaq.com/videos. We have all of them there. And finally, if you've still got questions or you need additional support, or maybe even you've got a suggestion for a future webinar topic, please email us at support@ueidaq.com or give us a call at 508-921-4600. We hope you found today's webinar useful, and we will see you again in September. Once again, thank you all for joining us, and I hope you enjoyed the last few weeks of summer if you can. And as always, please stay healthy.